Inside every computer, there is a strict divide between the abstract world of binary math and the physical reality of hardware. To store data, we have to translate millions of logical ones and zeros directly onto a physical surface, like a spinning magnetic disk. The engineering challenge is synchronization. The electronic sensors reading that disk must stay perfectly aligned in time with the mechanical rotation of the platter, even when reading long, silent stretches of empty data. If the drive simply wrote a continuous sequence of zeros, the reading hardware would eventually drift out of phase and lose its place. To prevent this, the binary stream is heavily encoded into a specific rhythm of magnetic pulses. Storing information requires a precise alignment of physical geometry and electromagnetic timing. To physically map that information, drive manufacturers rely on a universal coordinate system. This diagram illustrates a standard disk surface. The storage area is divided into tracks, concentric rings of data wrapping the center. These tracks are subdivided by angle into sectors. A sector is a discrete block holding a specific payload, typically 512 or 1024 bytes. By specifying a track number, moving inward from the edge, and a sector number, rotating around the platter, the drive electronics can mathematically pinpoint any specific byte of information. But this geometric map only tells the drive where to look. It does not explain the physical process of how that data bonds to the iron platter. The baseline method for writing data to a disk is a magnetic recording technique called non-return to zero, or NRZ. This chart plots a binary data sequence against the magnetic flux generated by the write head. Notice that the magnetic field never returns to a neutral zero state. The flux density is so intense that it completely saturates the surface of the disk. This automatic saturation overwrites any prior data, eliminating the need for a separate mechanical erase head. Because the field is always fully saturated, the absolute strength, or amplitude, of the magnetic charge contains no actual data. The system only records the exact moment the magnetic field reverses direction. Information is stored purely in the placement of that polarity shift, which makes the disk highly resistant to background noise. Relying strictly on the timing of these shifts creates a severe logical vulnerability. If the computer saves a long string of identical zeros, the magnetic field remains static, and the read head receives no timing signals at all. Without regular polarity shifts, the electronics recapture the data using a phase-locked loop. During a long sequence of identical bits, that loop loses synchronization, making it impossible to determine where one bit ends and the next begins. Drive engineers solved this timing drift by employing an algorithm called modified frequency modulation, or MFM. This diagram shows how MFM structures a single bit of information. On a double-density disk, each bit time is a strict 2.0 microsecond window. That window is divided exactly in half, one section designated for a clock pulse and the other for a data pulse. The encoding follows strict rules. Rule 1. If the data is a logic 1, it always receives a pulse in the data window. Rule 2. If the data is the first logic 0 in a sequence, it receives absolutely nothing, no data pulse and no clock pulse. Rule 3. For the second and all subsequent logic zeros in a row, a pulse is injected into the clock window, but the data window remains empty. By artificially inserting a clock pulse during long strings of zeros, MFM guarantees the read head encounters a physical magnetic shift frequently enough to maintain exact synchronization. This algorithmic modulation keeps the hardware on track. However, allocating dedicated physical space for clock pulses directly limits the density of data that can fit onto a single track. To increase capacity without altering the physical magnetic platter, manufacturers move to a different encoding scheme, run-length limited, or RLL. The RLL standard eliminates the rigid clock and data windows of MFM. Instead, a common variation called RLL27 uses mathematics to ensure that the run of consecutive zeros is strictly limited between 2 and 7. Before any information hits the drive electronics, the raw binary input is parsed through a conversion table, translating it into a highly optimized pulse sequence. These stacked timelines compare the physical track space required to write a specific binary string. The top sequence uses standard MFM, while the bottom shows the exact same data encoded with RLL. Because the signal pulse width has been slightly reduced, 3 RLL pulses fit into the exact same horizontal distance previously occupied by a single clock and data pulse. Upgrading the encoding math allowed engineers to pack 27 sectors onto a track that previously held 18, yielding a 50% capacity increase on identical magnetic hardware. Pushing data density to these extremes places immense pressure on the mechanical components retrieving it. Early floppy disks were built with flexible, semi-rigid jackets that offered minimal protection and operated under severe physical constraints. A floppy drive rotates at a slow 300 revolutions per minute, with the read head physically scraping against the magnetic surface. Hard disk drives isolate the platters in rigid enclosures and spin them up to 15,000 RPM. This extreme rotational speed is necessary for a mechanism called a flying head. The velocity creates a microscopic film of air that carries the read-write assembly just above the platter, completely eliminating mechanical friction. Removing friction removes wear, but introduces the risk of a head crash. If power is abruptly interrupted, the head can drop and physically scar the magnetic surface. To prevent this, drives employ an auto-parking routine to quickly retract the heads to a safe landing zone. Modern enclosures stack multiple platters on a single spindle. A vertical column of aligned tracks across the top and bottom of every platter is grouped into a logical unit known as a cylinder. Moving between these cylinders requires rapid physical actuation. Older drives relied on slow, noisy stepper motors that ticked across tracks mechanically. Modern designs use a voice coil mechanism, utilizing closed-loop servo feedback to monitor the signal amplitude and execute fast, sweeping corrections to the head position. Replacing physical friction with aerodynamic lift and precise servo motors allowed the read mechanics to successfully intercept the massively compressed, high-speed data streams generated by RLL encoding. Even with optimized mechanics and mathematics, the ultimate bottleneck is the electrical interface ferrying data to the motherboard. Older parallel standards like Integrated Drive Electronics, or IDE, eventually gave way to the serial ATA connection. This chart shows the physics logic inside the SATA protocol. Engineers drastically increased the transfer rate by lowering the electrical threshold for a logic 1 from 5 volts down to half a volt. Traveling up to half a volt requires less time than traveling up to 5 volts. Shrinking that electrical distance cuts the switching time, allowing serial interfaces to push transfer speeds up to 600 megabytes per second. Solid-state formats like USB flash drives bypass physical limits entirely. They contain no mechanical actuators, yet the operating system interacts with their serial memory using the exact same track, sector, and file allocation table logic designed for spinning iron. Optical memory stores data by burning microscopic physical pits into a plastic disc. To increase the storage density for formats like Blu-ray, manufacturers had to upgrade from red lasers to higher-frequency blue lasers, which can resolve a much tighter physical footprint. Whether reading physical pits with lasers, accessing floating gates and flash arrays, or sweeping heads over magnetic platters, overall speed is dictated by the interface voltage and the physical density of the medium. Retrieving a single file requires an incredibly fast chain of physical events. The interface pulses its serial voltage, the voice coil sweeps the actuator, the head stabilizes over the cylinder, and the magnetic flux shifts are read directly off the sector. The entire architecture relies on 3 interconnected pillars: a mapped physical topology, frictionless mechanical actuation, and mathematically precise signal encoding. A high-speed servo motor floating over a 15,000 RPM platter accomplishes nothing without the underlying synchronization rules of MFM and RLL to make sense of the binary silence. Over the decades, every generational leap in data storage has been an exercise in either overcoming mechanical friction or shrinking the electromagnetic footprint of a single bit. Computer memory continues to evolve, pushing the physical limits of hardware to perfectly synchronize mathematical logic with physical reality.